The moment you flip a switch and a dark room instantly fills with light, your mind tells a simple and powerful story about what just happened. You imagine something rushing through the wires. You picture tiny charged particles leaving the power source, racing down long metal paths and arriving at the bulb almost instantly. The speed must be enormous because the effect feels immediate. The image is so natural that it rarely feels like a guess. It feels like common sense. This common sense picture is the big misconception about electricity that Richard Feynman worked hard to dismantle. Electrons is not a fast river of electrons shooting from one place to another. Electrons do move in a conductor, but their average net motion in ordinary electrical circuits is astonishingly slow. In many household situations, the drift speed of electrons through copper wire is less than a millimeter per second. That is slower than a crawling ant, slower than the growth of a fingernail, slower than almost anything you would associate with the word electric. If electrons move that slowly, then something in the usual story must be wrong. Because when you flip a switch, the light does not wait minutes or hours for electrons to arrive. The bulb responds almost immediately. Even across large distances, electrical systems react on timescales that make the electron river picture impossible. To understand what electricity truly is, we have to let go of the comforting idea that electric current is mainly about fast-traveling particles and replace it with a deeper and more abstract understanding. From early education, electricity is described using the language of flowing fluids. Voltage is compared to pressure. Current is compared to flow. Resistance is compared to friction. Wires are treated like pipes. This analogy is useful because it allows beginners to predict how circuits behave. If you increase voltage, current increases. If resistance rises, current falls. The mathematical relationships are correct, and the analogy provides intuitive grip on equations. But analogies quietly shape the way we think, and sometimes they plant misleading images so deep in the mind that even years of study do not uproot them.
Water flowing in a pipe consists of molecules traveling from one end of the system to the other. If colored dye is injected at one end, it will eventually emerge at the opposite end. The matter itself migrates across the entire length of the pipe. If electricity worked that way, then when a generator in a power plant started producing energy, electrons would have to physically move through transmission lines across cities and fields and finally into your home before your devices could function. That would not produce instantaneous results, and yet everyday observation shows that electrical systems respond with extraordinary rapidity.
The key to resolving this tension lies in distinguishing between the motion of charge and the propagation of influence. Inside a metal conductor such as copper, the atomic structure forms a repeating lattice of positive ions. The outer electrons of the atoms are not tightly locked to individual nuclei. Instead, they inhabit a collective state that allows them to move through the material. These conduction electrons are constantly in motion, even when no battery is connected. Their motion is chaotic and random due to thermal energy. At room temperature, electrons zip around at high speeds, colliding with vibrating ions and with each other. But because their motion is symmetrical in all directions, there is no net current. When a battery or a generator is connected across the ends of a wire, it creates a difference in electric potential. This potential difference establishes an electric field inside the conductor. The field exerts a force on each conduction electron. The response of the electrons is not to suddenly accelerate endlessly down the wire because collisions occur constantly. After each brief acceleration, electrons scatter off the lattice, losing the gained momentum, and then accelerating again under the influence of the field. The result of countless collisions is a small average drift velocity superimposed on their chaotic thermal motion. This tiny directional bias constitutes electric current. The drift velocity is remarkably small in a typical copper wire, carrying several amperes of current. The net drift might be fractions of a millimeter per second. In thicker wires with heavy currents, the speed can increase, but it remains minute compared to everyday notions of rapid motion. It can take a single electron many hours to move a single meter along a conductor. Under ordinary conditions, that fact alone dismantles the idea that electrons from distant sources must rush into your lamp each time you switch it on. The moment the switch is closed, an electric field is established throughout the circuit, and it is the establishment of this field that propagates rapidly. The change in the electromagnetic field travels at a large fraction of the speed of light, depending on the properties of the surrounding materials and the geometry of the conductors. This propagation is not the movement of matter across the circuit, but the adjustment of a field configuration in space. Electrons already present everywhere in the wire respond almost simultaneously to the presence of the field and begin their slow drift. No individual electron needs to make the journey from the battery to the bulb for the bulb to shine. The electrons within the filament were already there long before the switch was touched. To shift intuition away from the fast particle story, it sometimes helps to imagine a long tube filled tightly with marbles. If you push one marble into one end, another marble emerges from the other end. Almost immediately, the marble you inserted does not travel the full distance. Instead, the push is transmitted through the chain. Each marble shifts slightly, and the effect appears at the far end without requiring rapid long-distance travel by any single piece of matter. This analogy moves thinking in the right direction, but even it is incomplete because it relies on mechanical contact and electricity. The agent transmitting influence is not solid contact, but the electromagnetic field which permeates space around and inside the conductor. The idea of fields requires a conceptual leap. A field is not a substance in the ordinary sense. It is a condition of space that assigns values such as electric strength or magnetic intensity to every point. When a charge is present, it modifies the electric field in the surrounding region. Another charge placed nearby feels a force. Because of the local field at its position, there is no need for direct contact or for the first charge to physically reach the second. Instead, the interaction is mediated by the field that exists throughout space. This view replaced the older notion of action at a distance and became one of the great unifications of 19th century physics. When current flows through a wire, a magnetic field circles around the conductor. At the same time, the electric field associated with voltage extends along the length of the wire and into the surrounding space. The combination of electric and magnetic fields carries energy. The mathematical expression describing this flow of energy is known as the Poynting vector, which shows that the direction of energy transfer is perpendicular to both the electric and magnetic fields.
In the case of a simple wire, the energy flows mainly through the space surrounding the conductor, guided by the structure of the circuit.
This assertion often surprises students because it contradicts the naive picture of energy being transported inside the metal, like cargo on a train. Yet careful calculation shows that the density of energy flow is concentrated in the region around the wire, rather than solely within it. The conductor serves as a guide, shaping the electromagnetic field pattern. The presence of free charges ensures the correct boundary conditions so that the field lines arrange themselves in a configuration that channels energy from source to load efficiently. Without the conductor, the fields would spread freely and radiate into space. Instead, the wire constrains them, forming a kind of pathway through which electromagnetic energy moves. Consider a simple circuit consisting of a battery connected to a resistor by two wires. The battery establishes a potential difference. When the circuit is closed, an electric field appears not only inside the wires, but in the space between them. The moving electrons in the wire create a magnetic field around each conductor. The interaction of these fields results in energy flowing from the battery through the surrounding space and into the resistor. Inside the resistor, electrons collide more vigorously with atoms, transferring energy as heat. This conversion does not require electrons from the battery to travel into the resistor. Instead, local electrons absorb energy delivered by the electromagnetic field. The deeper lesson here is that energy is not necessarily tied to the long-distance migration of matter in electromagnetism. Energy resides in fields. Fields can store energy and transport energy. Momentum also resides in fields. The electromagnetic field is not merely a bookkeeping device invented for calculation. It has physical reality because measurable quantities such as energy density and pressure can be attributed to it. The misconception about electricity arises partly because everyday experiences emphasize tangible moving objects. We see rivers flowing, and we imagine electricity must be similar. Since electrons are particles, it feels intuitive that their collective rush must constitute electrical action. Yet the true drama of electricity unfolds in the invisible configuration of fields that adjust with astonishing rapidity across space. This understanding becomes even clearer when examining alternating current systems. In most homes, the direction of current reverses 50 or 60 times per second. Electrons in the wire oscillate back and forth within a tiny range, rather than streaming steadily in one direction across kilometers of cable. If the water flow analogy were accurate, then alternating current would imply water molecules moving back and forth in a pipe, delivering net energy without overall displacement across the length. That sounds strange, yet it highlights the difference between matter transport and energy transport. In alternating current, the energy transmitted from power plant to appliance does not require electrons to migrate from source to destination. Instead, energy moves through time, varying electromagnetic fields guided by conductors. If one traces the history of electromagnetic theory, a remarkable narrative unfolds in the 19th century equations formulated by Maxwell unified electricity and magnetism into a single framework and revealed that changing electric fields create magnetic fields and changing magnetic fields create electric fields. These coupled variations allow electromagnetic waves to propagate through space at a speed determined by fundamental constants of nature. That speed turned out to be exactly the speed of light, revealing that light itself is an electromagnetic wave. The same equations governing currents in wires also govern the propagation of sunlight through vacuum. This unity demonstrates that electricity cannot be confined to the image of electrons rushing along metal. Light travels through empty space without wires, without pipes, and without flowing particles. In the classical sense, it consists of oscillating electric and magnetic fields, sustaining each other as they propagate. Recognizing that circuits operate under the same fundamental laws dissolves the false distinction between electricity in wires and radiation in space. They are manifestations of one electric field, behaving in different configurations. Understanding electricity correctly requires accepting that influence propagates through fields at finite speed. Information about changes in a circuit travels as a wave in the electrostatic field. This wave establishes new conditions throughout the system, causing charges at each location to respond locally. The rapid lighting of a bulb is therefore explained not by speedy electrons racing from the generator, but by the swift propagation of field changes that organize local electrons into motion. The conceptual shift from substance to interaction is profound. Electricity is not a stuff that fills wires. It is the behavior of charged matter interacting through a field that permeates space. When we say current flows, we are describing the net drift of charge under the influence of an electric field. When we say energy is delivered, we are describing the movement of electromagnetic energy guided by the geometry of the circuit. These are related but distinct descriptions, and confusing them gives rise to the big misconception. Why does this misconception persist even among educated individuals? Because the simplified language works for many practical problems. Engineers can design circuits using voltage and current without explicitly visualizing surrounding fields at low frequencies and short distances. The field picture reduces mathematically to relationships between current and voltage that resemble fluid flow analogies. Practical success reinforces the intuitive model even if the deeper reality differs. However, as frequencies increase or as systems become large, the field perspective becomes unavoidable. Transmission lines behave. According to wave equations, reflections occur when impedances are mismatched. Antennas radiate energy intentionally into free space. None of these behaviors can be fully understood through the water pipe analogy. They require thinking in terms of propagating electromagnetic fields. Confronting this reality enriches rather than diminishes our appreciation of electricity. It reveals that the flick of a switch engages principles that govern radio communication, radar, microwave ovens, fiber optic systems, and even sunlight warming the earth. The same field equations operate in each case. Whether energy travels along copper or across interplanetary space, it does so through structured variations of electric and magnetic fields. When you next imagine electricity racing through a wire, pause and reconsider. The electrons are indeed moving, but slowly. Their movement enables a configuration of fields to exist. The rapid element in the process is the propagation of electromagnetic influence across space. Energy glides through the surrounding region, guided by conductors, shaped by boundary conditions, and absorbed by devices that convert it into light, heat, motion, or sound. The big misconception dissolves once you separate the motion of electrons from the motion of energy. The electrons drift like a slow crowd responding to a signal. Energy travels as a swift reorganization of the electromagnetic field. The immediate glow of a lamp is not the triumph of particle speed, but the triumph of field interaction unfolding across space with extraordinary elegance. This clearer picture is not merely philosophical refinement. It aligns everyday electrical experience with the grand structure of modern physics. It shows that what appears simple is supported by a framework that unites circuits with waves and matter with radiation. It invites us to see wires not as pipes for rushing particles, but as guides for invisible fields that carry energy in ways both subtle and astonishing.
What really moves when current flows?
If the first misconception about electricity is that electrons race through wires at incredible speeds, then the second misconception is even more stubborn and more subtle. It is the belief that energy itself must travel inside the metal carried directly by those electrons from one point to another. The mental image is powerful. Electrons leave a battery loaded with energy, they travel through a wire, and they deliver that energy into a device where it is released as light, heat, or motion.
That image feels mechanically satisfying because it mirrors everyday experience. When a truck transports goods, the goods are physically inside the truck. When water carries debris, the debris is within the stream. So we assume that when electricity powers a heater, the energy must be inside the electrons moving through the conductor.
This assumption is not only inaccurate, it conceals the most extraordinary aspect of electromagnetic theory. The electrons are participants, but they are not the primary carriers of energy across space. The deeper reality is that energy resides in the electromagnetic field, and it flows through the space surrounding the conductor guided by the structure of the circuit. This insight, which follows directly from Maxwell's equations, transforms the way electricity must be understood.
Yes, we need to look more closely at what happens inside a conductor when a steady current is established. Copper wire, for example, is not empty space filled with free particles racing in straight lines. It is a crystalline lattice of positively charged ions arranged in a repeating pattern. Valence electrons occupy quantum states that allow them to move across the entire material, but they constantly interact with the vibrating lattice. These vibrations increase as temperature rises, which is why resistance grows with heat.
When no external voltage is applied, the conduction electrons are in dynamic equilibrium. They move randomly with high velocities, yet their motion averages to zero, net flow, because the random directions cancel one another out. The instant a potential difference is applied, an electric field appears. Within the conductor, that field exerts a force on every conduction electron simultaneously, across the entire length of the wire. The electrons respond by slightly biasing their random motion in the direction opposite the field. Since electrons carry negative charge, they drift opposite to the direction defined as conventional current. Each electron accelerates briefly under the field, then collides with lattice ions scattering, and losing directional momentum. Then it accelerates again. The repeated cycle of acceleration and scattering leads to an average drift velocity that is small compared with thermal velocity. This process of collision is also the origin of electrical resistance, because energy gained from the field during acceleration is transferred to the lattice during collisions, increasing the vibrational energy of the ions and thereby raising temperature. Now consider the question of energy flow. Suppose a battery is connected to a resistor by two long parallel wires. The battery's chemical processes separate charges, maintaining a potential difference between its terminals. When the circuit is completed, charges in the wires rearrange in response to the electric field established along the conductors. That field is not confined inside the wire, it extends into the surrounding space between the two wires. There is also a magnetic field generated by the moving charges in the conductors, forming circular patterns around each wire. The presence of both electric and magnetic fields means that electromagnetic energy density exists in the region around the wires. According to classical electrodynamics, the rate and direction of energy flow at any point in space is given by the Poynting vector, which is defined as the cross product of the electric and magnetic fields scaled by constants. The crucial consequence is that the direction of energy transport in a simple circuit lies mainly in the space outside the conductor, directed from the battery toward the resistor. This statement can feel almost unbelievable at first exposure because it contradicts years of intuitive conditioning. Yet careful calculations and experiments confirm it. If one analyzes a coaxial cable carrying current, one finds that the energy flows in the dielectric region between the inner and outer conductors, not inside the metallic cores. The conductors act as boundaries shaping the fields, but the energy itself is conveyed through the field configuration in the surrounding region. Imagine standing near a pair of parallel wires powering a device. There is a small electric field between them and a magnetic field encircling them. Although invisible, these fields represent physical energy in space. If one could visualize the pointing vector arrows, they would point from the source along the line of the wires and into the load. The load absorbs this energy, converting it into heat, light, or mechanical work. Inside the load, collisions between electrons and atoms dissipate the ordered energy delivered by the field into random thermal motion. Notice how this reframes the role of electrons. And electrons do not act like mail carriers, transporting packets of energy from origin to destination. Instead, they collectively create conditions that allow fields to exist and to transport energy efficiently. When energy enters the resistor, it is not because electrons that originated in the battery have carried it there. It is because the electromagnetic field has delivered energy into the volume of the resistor, and local electrons have interacted with that field, transferring its energy to the lattice. This distinction becomes even clearer when analyzing alternating current at 60 hertz. For example, electrons in household wiring oscillate back and forth about their equilibrium positions with extremely small amplitudes. They do not drift steadily from the power plant to your home. They simply shuffle microscopically in response to the oscillating electric field, yet your heater may be consuming thousands of watts of power continuously. How is that possible if electrons are not traveling long distances transporting energy? The answer is that the oscillating electromagnetic field propagates through the transmission lines at near light speed, and the energy flow associated with this oscillation is directed toward the load. The electrons serve as agents that allow the conductor to sustain these field configurations, but they themselves undergo only minute displacements. The energy does not depend on net migration of charged particles across the grid. To further illuminate this, consider a transmission line stretching many kilometers. A power station at one end generates alternating voltage. The change in field travels down the line as a wave determined by the line's inductance and capacitance. Per unit length, energy is stored partially in the magnetic field, associated with current, and partially in the electric field, associated with voltage. As the wave travels forward, energy flows in the dielectric surrounding the conductors, not inside the metallic material in the naive sense. If the line is properly terminated in a load that matches its characteristic impedance, the wave is absorbed without reflection and energy is delivered efficiently. If the load is mismatched, part of the wave reflects back, producing interference patterns along the line. These behaviors are inherently wave phenomena, and they cannot be adequately described by the metaphor of water flow. Through pipes, they belong to the dynamics of fields in space. The deeper you analyze electric circuits, the more unavoidable the field perspective becomes. Engineers dealing with radio frequencies, microwave systems, or high-speed digital signals must think in terms of electromagnetic waves. Even in printed circuit boards, traces behave like miniature transmission lines at high frequencies. Designers must consider propagation, delay, reflection, and field coupling between conductors. In such contexts, the simplistic idea of current as moving charges within a wire is insufficient and sometimes dangerously misleading. Returning to the microscopic scale, inside a conductor, another layer of complexity appears. From quantum mechanics, conduction electrons are not classical particles bouncing around freely, but quantum entities occupying allowed energy states, determined by the periodic lattice of ions. Their collective behavior gives rise to band structure, explaining why some materials are conductors and others are insulators. In conductors, partially filled bands permit electrons to respond to applied fields, resulting in current. In insulators, band gaps prevent such movement under ordinary conditions. Although quantum theory refines our understanding of electron behavior, it does not overturn the essential classical conclusion about energy flow. Fields remain the carriers of energy, even when the field itself is quantized at a deeper level. The classical Poynting description approximates the flow of electromagnetic energy in macroscopic circuits remarkably well. The microscopic processes of scattering and resistance merely determine how energy delivered by fields is converted into heat or other forms. One might ask why the field interpretation feels so unintuitive. Part of the reason is that we cannot see electromagnetic fields directly. We see the consequences such as glowing filaments or spinning motors, but we do not perceive the surrounding field lines with our senses. Because fields are invisible, we tend to imagine tangible objects moving. Instead, the electron appears easier to picture than an electric field distributed across space. Yet invisibility does not imply unreality. Gravitational fields are invisible, yet they govern planetary motion. Air pressure is invisible, yet it exerts measurable forces. Electromagnetic fields are as real as any physical entity because they possess energy, momentum, and measurable influence. Instruments can detect field strengths. Radiation pressure can push on surfaces. Light can exert force precisely because its electromagnetic field carries momentum. Recognizing that energy resides in the field reshaped the narrative of electrical power generation. When a turbine spins inside a generator, coils of wire rotate within magnetic fields, altering the flux through the coils. According to Faraday's law, this change induces electromotive force, establishing electric fields in connected circuits. Those fields propagate through conductors at high speed, setting up patterns of energy flow outward from the generator. The generator does not inject electrons that travel vast distances. Instead, it modifies the electromagnetic field across the network, thereby enabling energy to be transported to loads wherever they may be. The elegance of this view extends further because it unifies the behavior of circuits with the nature of light. Light itself is an electromagnetic wave propagating through space. Without need for a material medium, when sunlight warms Earth, energy travels 93 million miles through vacuum, carried entirely by oscillating electric and magnetic fields. That same type of energy flow, albeit confined and guided, occurs in a simple lamp cord in your home.
The difference is one of geometry and frequency rather than fundamental principle.
Once you internalize this perspective, the act of flipping a switch acquires new meaning. At the instant of closure, charges redistribute along conductor surfaces, establishing boundary conditions that shape the electric field between wires. The magnetic field rises in response to current. The interplay of these fields defines the direction of energy transfer from source to load. The electrons move slowly, yet the reconfiguration of fields races across the circuit at near light speed, ensuring that energy delivery begins almost immediately. It is essential not to overcorrect the misconception by denying the importance of electrons. Their motion is indispensable because without mobile charge, the necessary boundary conditions for sustaining fields would not exist. A vacuum tube without conductors would not guide energy in the same constrained way. The conductor provides a structure that channels the field. Preventing energy from radiating inefficiently, the electrons also mediate the transformation of field energy into thermal or mechanical forms within loads. However, electrons are mediators rather than transport vessels. The energy they help convert arrives via the field. Surrounding space participates actively in the transfer, even if it appears empty. Fields are not decorations around wires. They are the real stage upon which the drama of energy transmission occurs. Understanding what truly moves when current flows corrects more than a classroom misconception. It opens the door to a coherent view of electromagnetic phenomena ranging from power grids to radio transmitters, from fiber optics to microwave ovens. It shows that electricity is fundamentally about dynamic field configurations, whose evolution in time and space governs the transfer of energy throughout our technological world. When you picture two simple wires connected to a resistor, visualize not a stream of particles rushing like water, but a flow of electromagnetic energy in the region around them. Directed steadily toward the resistor, imagine electric field lines stretching between the wires and magnetic field circles wrapping around them. Together they define an invisible current of energy moving swiftly through space, while electrons inside the metal drift quietly like participants in a vast coordinated response. This is what truly moves when current flows, not primarily electrons traversing distances, but energy encoded in fields shaping the behavior of matter across space. The conductor is the guide, the charges are the responsive agents, and the field is the carrier. The sooner this distinction becomes intuitive, the sooner the big misconception about electricity dissolves into a clearer and more unified understanding of how nature actually works. The field is the reality. By now, the familiar image of electricity as a stream of fast-moving electrons should feel unstable. The slow drift of charge, the rapid propagation of influence, and the flow of energy through surrounding space have already begun to replace the older mental picture. Yet there remains a deeper shift that must occur if the misconception is to be fully dissolved. That shift concerns what we consider to be fundamentally real. For centuries, physics was built on the idea that matter is primary and forces are secondary. Objects push or pull one another through some mechanism that may not be visible, but is nonetheless imagined as a connection between solid things. The early models of electricity followed the same pattern. Electric charge was treated as a kind of fluid contained within matter, and electrical effects were described as movements of that fluid. The field was introduced later as a mathematical convenience to describe how forces vary from point to point. But as understanding deepened, the field refused to remain a mere bookkeeping device. It acquired energy, it carried momentum, it exerted pressure, it propagated in waves across empty space. It became clear that the field is not simply a description of how charges influence one another. The field is an entity with physical properties of its own. This is the final and perhaps most radical correction to the misconception about electricity. The wire is not the central actor. The electron is not the hero. The field is the true protagonist. Consider again the act of closing a switch. When the connection is made, charges rearrange themselves almost instantly along the surfaces of conductors, establishing boundary conditions that determine how the electric field threads through the space between wires. The magnetic field rises as current begins to flow. These fields do not exist as isolated decorations, but as an intertwined structure filling the surrounding region. The pattern defines how energy moves and where it will be delivered. The speed at which this pattern adjusts is not determined by how quickly electrons can drift through copper. It is determined by the electromagnetic properties of space and materials encoded in Maxwell's equations. Those equations reveal that disturbances in the electromagnetic field propagate at a speed fixed by two constants, the electric permittivity and magnetic permeability of free space. Their combination yields the speed of light. This was one of the most stunning revelations of 19th century science because it implied that light itself is an electromagnetic phenomenon. When light travels through vacuum, nothing material accompanies it. No electrons carry its energy across the void. Instead, oscillating electric and magnetic fields sustain each other in a self-propagating wave. Energy rides on this oscillation, moving through space without any material medium. The same mathematics describing the glow of a lamp cord describes the sunlight crossing millions of miles. Recognizing this continuity changes how electricity and wires must be viewed. The wire does not confine electricity as a pipe contains water. It shapes the electric flow. It shapes the electric flow. The second bomb with losh commercial regattiri. Without that, it's say what you succeed after chewa that could no qua arrived. Some of you never on so like the boxing miscontinuity changes how electricity and wires must be viewed. The wire does not confine electricity as a pipe, contains water. The electriso is to explain each cat. It shapes the electric flow. And then the one annihilation put up the actation was scoring each paras. That rearrangement it shapes the electric. That rearrangement the wasteful. And in your imagine removing the wire entirely and allowing a battery to sit with its terminals exposed in open space. Charges would accumulate on the terminals and create electric fields around them, but without a complete circuit. Little sustained energy transfer would occur. The conductor provides the path along which a stable field configuration can form, connecting source and load. The electrons are required because they allow rapid redistribution of charge at surfaces and sustained current inside the metal. Yet the energy that ultimately powers a device flows through the field pattern, extending in space. To appreciate how real this field is, consider that it possesses measurable energy density, given by expressions involving the squares of the electric and magnetic field magnitudes. If you create a strong electric field between two plates of a capacitor, you have stored energy in the region between them. Even if no electrons are moving across the gap, in an inductor energy is stored in the magnetic field surrounding the coil when current flows.
These are not metaphors, but quantitative facts confirmed by experiment.
Furthermore, the electromagnetic field carries momentum. Radiation pressure exerts force on surfaces because the field transports momentum along with energy. Solar sails proposed for space travel rely on this principle. Photons striking a reflective surface impart momentum, even though they have no mass. In the conventional sense, the field thus fulfills roles traditionally reserved for matter. In electrical circuits, the field can also be said to possess inertia in a distributed sense, because energy stored in inductance and capacitance causes delays in oscillations. When a circuit is switched on, transient waves propagate, reflecting and settling before reaching steady state. These behaviors arise from the dynamic evolution of the field configuration, not from sluggish electrons traveling down wires. Another way to confront the field's reality is to examine how electromagnetic signals propagate along transmission lines. A pair of parallel conductors separated by an insulating medium forms a structure that supports waves. The electric field exists primarily between the conductors while the magnetic field wraps around them. Energy flows along the line in the surrounding region. The conductors determine the boundary conditions, forcing the fields to assume shapes consistent with the line's impedance. If the line is terminated properly, the wave is absorbed. If not, reflections occur and standing wave patterns form in space around the wire. In radio antennas, the conductor is deliberately shaped to allow energy to detach from guided form and radiate outward as free electromagnetic waves. The antenna does not throw electrons into space at high speed. Instead, it shapes accelerating charges in such a way that the changing fields no longer remain confined, but propagate away independently. The energy leaving the antenna travels through vacuum as a wave of fields. Seen in this light, the earlier misconception appears almost quaint. It assumed that electricity is mainly about motion of tiny material objects inside metal. Yet the deeper truth shows that material charges and conductors are components of a larger electromagnetic structure that extends through space and evolves in time. Why is this shift so challenging psychologically? Because human intuition evolved in a world dominated by contact forces and visible matter. We trust what we can see and touch. Fields are invisible and intangible in everyday experience. We infer them from effects. Therefore, we instinctively treat them as secondary to the particles whose behavior we can imagine more concretely. However, modern physics increasingly reveals that fields may be more fundamental than particles. In quantum field theory, particles themselves are excitations of underlying fields. The electron is not an independent tiny billiard ball existing apart from space, but a localized excitation of the electron field. Photons are excitations of the electron field. Photons are excitations of the electron beat. Photons are excitations of the electron Photons are excitations of the electron field. Photons are excitations of the electromagnetic field. In this view, fields are primary and particles are manifestations of those fields, in particular quantized states. Even without venturing deeply into quantum theory, the classical understanding already demands respect for the field as real. When you plug a device into an outlet, you engage a vast electromagnetic spanning cities and continents. The generators alter field configurations on a grand scale, and those changes propagate swiftly across the network, enabling energy transfer to countless loads simultaneously. No physical river of electrons flows from a central reservoir to each appliance. Instead, a synchronized field structure connects them. There is also a profound implication concerning causality. Influences do not act instantaneously across distance. When a generator changes its output, the resulting change in field travels outward at finite speed. Nothing in the universe responds before the field perturbation arrives locally. This constraint preserves consistency with the principle that no signal can exceed the speed of light. The misconception that electrons race instantly through wires sometimes masks this deeper rule, but careful analysis always restores the primacy of finite propagation of fields. Another subtle consequence arises when considering energy conservation. If energy flows through the surrounding field, then the location and density of that flow can be mapped at every point in space around the circuit. Energy enters the resistor through the space adjacent to it, not through an invisible pipe inside the wire. The energy leaving the battery spreads into the surrounding region and then converges toward the load following paths determined by field geometry. The conductor ensures that this convergence is efficient, but the field describes the actual movement.
Experimental demonstrations using carefully designed apparatus confirm this picture.
Measurements of electromagnetic field distribution around conductors match theoretical predictions precisely. Engineers exploit these principles in designing shielding coaxial cables. waveguides, and microwave resonators. In each case, understanding the field configuration is essential to controlling energy flow. When electricity is taught only through circuit diagrams and algebraic relationships, students may succeed in solving problems without ever encountering the underlying field concept. Yet if one aspires to a coherent worldview, the field cannot remain hidden. The luminous filament in a bulb glows because electromagnetic energy delivered by fields is converted into thermal radiation. Visible light emitted by the filament is itself an electromagnetic wave, propagating outward into the room, carrying energy away through space. Thus, the same field that transported energy to the filament now carries energy from it as light. Seen from this perspective, the entire electrical process becomes a sequence of field transformations. Chemical energy in the battery rearranges charges, establishing an electric field. That field, combined with magnetic field patterns, transports energy through space to the filament. Collisions inside the filament convert field energy into thermal motion, which then creates oscillating charges that radiate new electromagnetic waves outward as visible light. The story begins and ends with the field. Let us return once more to the simple switch. If you close it, visualize not a torrent of particles sprinting down copper corridors, but a sudden reorganization of the electromagnetic environment across the circuit. Charges shift along surfaces, adjusting within nanoseconds. The electric field blossoms between conductors. The magnetic field grows around them. Energy begins to stream through surrounding space, guided toward the load. Electrons inside the wire respond, gradually drifting in compliance with the field and transferring energy to the lattice where needed. No individual electron carries a personal packet of energy from source to destination. Instead, the field serves as the universal courier, weaving through space at near light speed. The conductor is the architectural element that shapes this courier's path. This realization aligns electricity with the broader structure of physical law. It reveals unity where intuition once saw separate mechanisms. It shows that circuits, radiation, and even light from distant stars obey the same principles of field dynamics. It corrects the primitive picture of electricity as fast-moving stuff and replaces it with a more accurate and more profound vision of reality. In the end, the big misconception dissolves into a deeper appreciation. Electricity is not the story of rushing electrons, but the story of electromagnetic fields organizing and transferring energy through space. The field is not an abstract mathematical trick. It is the medium through which nature conducts the drama of energy exchange across the universe. And once that truth becomes clear, flipping a switch is no longer a trivial act, but a reminder that invisible patterns of field and matter are continuously shaping the flow of energy around us in ways far more elegant than our first intuition ever imagined.